Hello, hello, hello. I'm going to send you now the solutions to problem 49. And yes, it wasn't too difficult. However, even though all of you or most of you said, yeah, we used the JEE equation, but of course we knew how to derive it. I probably believe you. But for me there is a big difference between remembering that kinetic energy is 1/2 mv squared, remembering that F equals ma, remembering Newton's universal law of gravity, and remembering an equation that tells you what the E field is on the y-axis through the center of a charged ring. That's madness. And also an enormous waste of energy to remember that. So in any case, I'd like to think that those who use that, I call it JEE equation, but that's of course the wrong name. I'd like to think that most of you who use that equation looked it up first. Let me tell you, I probably know only 20 equations in physics off the top of my head. All others, all hundreds and hundreds of others, I either know how to derive, or if necessary, I know how to find them. So yes, it's okay that you looked up that bizarre equation, the JEE equation. That problem, this problem, 49, I had about 50% correct solutions. For those of you who said we could derive it, I believe you. And I bring that to a test. The next problem, number 50, has the same underlying basic physics as this problem. But I can assure you, you can't find an equation for that one. So, prove it now to me, that you can derive it. By the way, it took me about 10 minutes to derive problem 49. I first derived it, then I made some obvious checks. I substitute in my result y equals 0, and I also convinced myself that the magnitude of the E field is the same whether you use a numerical value for y that is positive and use the same numerical value whether y is negative. So I made those checks and I convinced myself that my answer was correct, and then I substituted in my answer the numerical numbers that I gave you. So all of that, yeah, took me 10 minutes. Some of you said took them only 2 minutes. Well, you may be better than I am. That's easy for me to accept. It took me 10 minutes. Problem 50 will take you more than 10 minutes. And I fear that many of you will get stuck. Will that give me great pleasure? No, not at all. My objectives are to teach you physics. And so my objectives with problem 49, with the ring, that objective was also to teach you physics. My objective was not for you to look up the result somewhere hidden in your notes and then send me an answer, because clearly that was not something I taught you. But yes, I accept it. I accept the fact that you looked it up. Problem 50? No way. No way you can look that up. So get ready. Have a nice day and take care. I fear that some of you may not want to be friends anymore after problem 50. I will post it approximately a week from now. Hello, 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 hello. The solutions to a very easy high school problem. We have here a ring which is a perfect circle, has a radius r, and it is a conductor, and we put a charge on that ring. Since it is a perfect circle and it is a conductor, the charge will distribute uniformly. We know the charge, we'll get back to that later. We call the charge Q for now. The radius of this ring is 0.5 meters. Here is the center of the ring, and here is a line perpendicular to the plane of the ring, going right through the center. We call this direction y, and we call this point y equals 0. And the question now is, what is the electric field at the center? Magnitude and direction. And what is the electric field at point P, which is 0.8 meters above the center? Again, direction and magnitude. Before we do any math, it should be immediately obvious that at the center of that circle, the E field is 0. Take any location here at the circumference, or at the ring I should say, a little bit of charge here, a little small fraction of this, right at the center, there is an electric field due to that little charge pointing towards the center. But on this side, there is one pointing in this direction. And so these two will cancel each other. And this one will cancel the E field from this location. And this one will cancel the E field from this location. So without going any further in details, be aware of the fact that each little small part of the ring will have an E field at the center, which is in the direction of the plane towards the center, but if you add all those vectors up, the net sum will be 0. So we can already predict, when we solve the problem for any value of y, that if y is 0, the E field better be 0. If not, we made a mistake. So now I'm going to solve the electric field at point P, and I will use only the symbol Q, the radius R, and Y. I call this simply Y. In this, let's call it horizontal plane, I have here an angle, very small angle, I call that angle delta theta. And where that angle reaches the circumference, the linear size here is RD theta. And so the amount of charge that is here is a very small fraction of this charge. And how small is clear. If the length here is rd theta, then the charge that is there, think of it as being dq, small amount of charge, that must be rd theta divided by 2 pi r times q. And you see that here, rd theta times q divided by 2 pi r. So, what is now the E field at point P, which is caused by this by this little bit of charge? So we use Coulomb's law, and it becomes then immediately obvious what the E field at point P is due to this charge alone. It is this charge, which is d theta rq over 2 pi r, divided by the distance square. Well, the distance square is y squared plus r squared, and divided by 4 pi epsilon 0. That's the famous 4 pi epsilon 0 that you see in Coulomb's law. Many books call 1 over 4 pi epsilon 0, they call that k. So there would be not a 4 pi epsilon 0 here, but there would be a k upstairs. So that is the E field in this direction. That is this E vector. However, if we add up all contributions from every little bit of charge here, then I claim that the net force of all those vectors will be in this direction, and the component in this direction, in this plane direction, will be 0. And that is very easy to see. So, this charge here has an E field in this direction, and in this direction also. That's the component, this is called the vertical direction, and let's call this the horizontal direction. This is the factorial sum of those two. Now take one here, a little bit of charge, the same charge that you have there. Well, there will be an E vector in this direction. And that angle here will be the same. And the horizontal component in the plane will be exactly the same as this one. And the vertical component, if I call that the vertical component in the y direction, will also be the same. But in the horizontal plane they are in opposite directions, so they kill each other. If you want to spend more time on it, that's fine. At least convince yourself that the factorial sum of all the charges, the E fields at this point of all these charges, will have 0 component in the horizontal plane, if I call that plane horizontal. So all we are interested in then, because that's the net vector of all the E fields, must be in this direction. It's upwards because the charge is positive. If the charge were negative, then of course it would be downwards. So, what do we have to do now to change the magnitude of this vector into this vector? We have to multiply it by the cosine of the angle alpha. Here is the cosine of alpha. And what is the cosine of alpha? That is y divided by this distance. And this distance is the square root of y squared plus r squared. So I'm going to take this and put that in here. And you see that there. Notice you see upstairs a q and a y. It is this y and it is this q. Notice that this r cancels out this r. So downstairs you have the 2 pi and you have the 4 pi epsilon 0. And now you have to take this term and multiply that by this term, which is part of the cosine. So that gives us then y squared plus r squared to the power 1.5. Okay? So dE, which is a teeny little fraction of the total E vector, is then this value, and this d theta is then this very small angle here. I called it therefore dE. But now we want to know the contributions of everything on the ring. Well, that's easy, because the integral that we have to do is we have to integral now over all angles theta, and so it is the integral from 0 to 2 pi of d theta. And that itself is of course 2 pi. And since that is going to be 2 pi, this 2 pi disappears, and what we end up now is that the E vector everywhere on this line will be upwards. The net sum of all these small E vectors will be upwards, and the magnitude is given by this. Notice there's y upstairs here. If you put in y equals 0, that E value is 0. It better be, because we argued already it had to be 0. And if y is 0 here, that doesn't change the situation. Downstairs is still finite, it's r squared. So now we are in business. We have already answered what the E field is at the center of the circle. So now we have to substitute in there that y is 0.8 and that q is 2.10, 2 microcurie, 2 times 10 to the minus 6, and that r is 0.5 meters. I had to look up 1 over 4 pi epsilon 0. In high school, we always used that 1 over 4 pi epsilon 0 is 9 times 10 to the power 9. But since I'm asking you for 3-digit precision, I decided to look it up. If you take 9 times 10 to the power 9, that would be still okay with me. It is 8.99 times 10 to the power 9, and that's what I have used. And so, using the values for y 0.8, for r 0.5, and using this value, I find that the E vector, the magnitude of the E vector at point P is 1.71 volts per meter, or if you prefer the units, newtons per coulomb, that's the same thing. So 3-digit precision is all I wanted. So 1.71 times 10 to the 4th. Alright, we all agree? It's simple. It's a little bit more math actually than physics. I repeat myself, why do I give this simple problem? For those of you who couldn't do this problem, or who did it wrong, no chance in the world that they could do the next problem. However, if they study my solutions, there is a fair chance that they can do the next problem, which is much harder than this one, but it is similar. So, I predict that 90% of you will do this correctly. Maybe I'm too optimistic, but I will not know when I'm taping this. I don't know yet your answers, because I record these problems and the solutions sometimes months before I post them. So right now I have no knowledge yet, even though you see the solution, I have no knowledge yet of how many of you did it correctly. Okay, so get ready for problem 2 and study this one if you didn't do it right. Have a nice day, take care, and surely we will be friends. want to add something to my solution. So we agree that at y equals 0, the E field is 0. And we also agree that at y equals 0.8 meters, this is the E field. Now, we should agree that if y is very, very large, the E field should be very, very small, because you're very far away from the charge q. So that means, if we increase y all the time, there should be somewhere on this line, through the center of the ring, this vertical line, there should be somewhere a point where the E field is a maximum. And I thought it would give you some insight if I add a little bit to it that covers this idea where this maximum would be. So what it comes down to is, if you look at this function, and we put in for r equals 0.5 meters, for what value of y is this function, y divided by y squared plus r squared to the power 3.5, for what value of y is that a maximum? Well, you can try to analytically solve that. I tried it, and I got stuck, to be frank with you. So you have to take the first derivative and make it 0. So I cheated a little, or actually I cheated a lot. I asked Wolfram to show me the curve for a function z, which is y divided by y squared plus 1/4, because r squared is a quarter, to the power 3/2. And within a second, Wolfram came up with that curve. And it runs exactly as you would expect. At y equals 0, the E field is 0. And then when you go further away from the horizontal plane through the center, it increases and it increases. It reaches a maximum and then it goes down again. And this curve is about to scale. Our value, y is 0.8 meters, gives us a value for that function of 0.95. However, very close to 0.35, but it is not an analytical solution, okay? I looked at the curve and I eyeballed it. So very close to y equals 0.35 meters. Is this function a maximum? And that maximum is then roughly 1.54. And so if you use that value of 1.54, then you find that at the highest electric field on that vertical line is then 2.77 times 10 to the 4th volts per meter. So it is higher. And the ratio between the E field here and the E field there is of course the ratio 1.54 divided 0.95. I think it's important that at least you get the idea that if the E field is 0 at the center and it must be 0 at infinity, then there must be somewhere a maximum if it is 1.7 times 10 to the 4th volts per meter at a distance of 0.8 meters. And that I wanted you to not only appreciate, but I even made an effort to give you a solution which is quantitatively very close to the exact value of y, where E at point P is a maximum. Okay?